Hello everyone, this is a presentation video based on my recent IEEE publication on the data-driven estimation of charge transport parameters. You can check out the paper for your reference and it's also provided in the description. Before we even step into the topic of the video, let's play a short game which will help you connect with what is going to be discussed in the upcoming slides. Now you have to guess the 2D shape in these images and most people will say that shape 1 and shape 2 are both circles. So in this case, shape 1 appears to be a chamfered square or a rounded edged square, while shape 2 appears to be a circle. In this image, it's very clear that shape 1 is a square and shape 2 is a circle. What I really did here was I took a picture of a square and a circle and I progressively blurred these images. The square turned into a rounded square and with further blurring it turned into a circle, while a circle remained a circle. So the human mind, which could differentiate between a circle and a square, could not differentiate when the image quality is very poor or when the image resolution is very poor. So this idea will come in handy during the presentation. So now let's formally introduce you to the topic. Ideally, insulators should not conduct electricity, but in reality, insulators do conduct a minute current in the form of electron and hole transport. The dynamics of charge evolution involves charge injection from the metal electrode into the dielectric and charge advection through the dielectric, recombination between electron and hole pairs, and finally charge extraction as the charge meets the counter electrode. So the charge injection happens through Schottky thermionic emission and is given by the first formula, and charge advection is characterized by the continuity equation and given by equation 2, and the total numerical flux is a sum of the convective flux and the diffusive flux, and this source term is just for representation of recombination dynamics. So the parameters such as mobility, diffusivity, and injection barrier potential, they determine the system evolution with time. For example, if the mobility or diffusivity is high, it means that the charge is going to transport itself faster in the insulation medium, and it also implies that the insulation quality is poor. So this not only determine their charge dynamics but also serve as an insulation health marker and are crucial for condition monitoring applications. So let's see how the charge evolution in dielectrics is experimentally measured, and from that information let's see how the transport parameters can be extracted. So in this schematic you can see a PA measurement system in which dielectric will be subjected to high voltage and high electric fields, and using pulsed electroacoustic technique it maps the spatiotemporal evolution of charge inside the dielectric as shown in figure 3a. So this is spatial variation and this is temporal variation, and blue represent negative charge which is electrons and red is hole charge, and as you can see that the holes move from anode to cathode with time and electron moves from cathode to anode with time. And traditionally, researchers used to tweak the charge transport parameters like mobility, diffusivity, so on. And the corresponding computational charge distribution will also vary. And the parameters for which there is a good resemblance between the experimental and computational space charge data will be considered as the true system parameters. But there is an issue. The above process is very complex. One needs to numerically evaluate the coupled system of ODEs and PDEs, and on top of that apply optimization techniques which will iteratively it will figure out the optimal parameters. So this is not at all suitable for edge computing applications. And as online condition monitoring of insulation systems gain importance, these traditional methods are impractical due to their computational intensity and limited adaptability for real-time implementation on embedded hardware. So embedded hardware systems are Arduinos, STMs, NXPs. These are common microcontrollers, and Arduino is a hobbyist microcontroller, but STMs and NXPs are the industry standard. So you can't run numerical integration and optimization in STMs and NXPs, which only have a few hundred kilobytes of memory, and they are also low power devices. So traditional methods for charge transport estimation cannot run on such low power hardware. Luckily, all hope is not lost, as there is an emerging trend in the computational physics community to use physics-informed learning techniques to predict and understand the behavior of complex systems even with a moderate quantity of data. So these models are trained with both the physics information, which are derived from the laws of physics, and the phenomenon information, which is the experimentally obtained data on the system dynamics. So here you can see that when you know a lot of physics about the system, only a small data is required to understand the behavior of the system. But when you have no physics at all, then you need a large amount of data to predict and understand the system behavior. Whereas when you have some data and some physics, you can apply physics-informed machine learning techniques to get the best of both worlds and estimate the system behavior. There are many such machine learning techniques which are used to understand the behavior of dynamical systems, but the star performer is the SINDI algorithm. It stands for the sparse identification of nonlinear dynamics, and it can be used to derive the characteristic equations of dynamical systems directly from measurement data. This model combines sparsity promoting optimization and nonlinear system identification to identify the most important dynamics that govern the behavior of system. So this is commonly adopted in fluid dynamics, for plasma dynamics, for chemical diffusion reaction systems, etc. Now let's take a formal look into the mathematics governing the SINDI algorithm. Any self-consistent dynamical system can be represented as dx by dt equals f of x, where x is the primary variable and f can be a linear combinations of any functions theta 1, theta 2, theta 3. In matrix form, this can be represented as x dot equals theta into zeta, where zeta are the coefficients of the functions in theta. So now if we had access to the data in x and we know a priori some functions in theta which can govern the dynamics of the system, then we may be able to estimate the coefficients of these functions through sparse regression process. This is the philosophy behind the SINDI algorithm, and that's exactly what the pioneers in the field, Brunton, Proctor and Kutz, have done. They have taken a Lorentz attractor, a dynamical system, the data of it, they have input in the SINDI algorithm and use sparse regression to identify the coefficients, and when they recomputed the dynamics, the reproduced dynamics closely resembled the complex system dynamics from which the data was built on, from which the model was built on. So this validates the proposed model. And it's great that now you need only the phenomenon data and now you can build a SINDI algorithm with it. In our case, we need to generate a space charge data that is a suitable input to the SINDI model. So we already know that we can solve this coupled system of differential equations to obtain a space charge density map. And with these parameters as the values for holes and electrons, we can generate a suitable data set. So here you can see that the space charge map that is obtained from the solution of the coupled system of differential equations, that is by solving the bipolar charge transform model. And intentionally I have added noise to make it mimic with the real experimental data. And further, to clean the data, I have used POD and reconstruction to remove the noise. As you can see here in the zoomed in portion, noise is significantly removed. And once noise is significantly removed, I segregate the data which is specific to hole and electron transport so that these are suitable inputs to the SINDI model. For the charge transport problem, the SINDI model can be formulated as follows. So rho dot is equal to theta of rho into zeta. And here the SINDI model assumes that the rate of change of space charge density is a sparse Rayleigh combination of candidate functions in theta whose coefficients are zeta. Since we intend to discover the equations of transport, we may be interested to embed the theta matrix with terms such as powers of rho, derivatives of rho or integrals of rho, or their polynomial combinations. We know that the algorithm works well with high resolution phenomenon input data, but does the SINDI formulation hold good for low resolution input? It turns out that if you saw that if these two conditions are satisfied, then the SIND algorithm can accurately estimate the charge transport parameters even when the data resolution is low. I'm not going to provide the proof for it here as it is already published in the paper. So the immediate question that comes into mind is, under what circumstances will those equations 15 and 16 be satisfied, and under what circumstances does 15 and 16 not hold good? So I tried a bunch of candidate functions to check if they are valid as per these conditions, and the candidate functions that satisfy 15 and 16 are rho, 1 is just a constant, all integrals and derivatives of rho, they satisfy 15 and 16. Whereas rho power n, where n is greater than 1, and sine of rho, cos of rho, and multiplicative combinations of rho and derivatives of rho, or rho and integrals of rho, so they do not satisfy conditions 15 and 16. So it turns out that the PDEs containing nonlinear terms do not satisfy the conditions, while the linear PDEs satisfy these conditions. So in layman's language, what it means is that if you have low resolution phenomenon data and the phenomenon is linear, then the SIND will accurately estimate your charge transport parameters. But if the phenomenon data is nonlinear and the data resolution is low, SIND cannot estimate the parameters accurately. But in the case of high resolution data, both linear and nonlinear PDEs can be estimated very well by SIND. So does this sound familiar? It should, because in the starting of the video I mentioned that the human brain was unable to distinguish between a circle and a square when the image was blurred. But if the image quality was sufficiently high, we had no problem in identifying between a circle and square. So this is similar to what we have here. Nonlinear PDEs under low resolution, SIND cannot identify it, whereas linear PDEs, irrespective of the resolution, SIND is able to identify it. And since the charge transport phenomena is nonlinear, SIND may perform poorly when the data resolution is low. Now let's get into the results on how to discover the charge transport equations using the SIND model. Here you have the pre-processed and segregated data, and this data you input to the SIND model and apply sparse regression to identify the sparse coefficients. If you input these coefficients into the assumed nonlinear PDE, you discover the PDE governing the system. But a question arises, how accurate are these results? Because we just proved that data resolution affects the accuracy of the SIND model. Which is why I performed an additional study by varying the resolution of the input data and see how the accuracy of the SIND algorithm varies. So here you can see that the high resolution data is being progressively blurred and it is being input to the SIND model to identify the variation in the results of the SIND model. And here the deviation from ground truth due to low resolution is described for both drift velocity and diffusivity. And at high resolution, you can see that the SIND estimates are very close to the ground truth. And as resolution lowers, you can see that it deviates from the ground truth. And at a point, the identification of the PDE itself becomes unsuccessful. So figure 13 describes the error due to progressive blurring. And as shown here, at high resolution, the error is just around 10%, that is, the accuracy is close to 90%. And as you blur the input data, the error increases logarithmically. Having a deep knowledge on how the model behaves with resolution, the SIND algorithm is put to test with the experimental data. So this is the experimental data obtained from pulsed electroacoustic measurements. The data is cleaned using POD, reconstruction and segregation, and input to the SIND model, and the same process is followed. We identify the sparse coefficients, we input it into the assumed nonlinear dynamics, and we get the PDE of the governing system. Here we have a comparison of SIND with the traditional BCT model of how good it performs. So here you can see that the average drift velocity and of holes and electrons is about 13 nanometer squared per volt second, and here the value is 34. Whereas here the benchmark values when compared to the benchmark values, these values are really low because it's 58 and 88, and we get an estimate of 13.5 and 34. Here also the estimate is lower than the benchmark value. Here it's 1.43 and here it's 2.42. Here it's 0.56 and there it's 2.17. But do we observe a pattern in all this? Here you can see that the electron drift velocity is lower than the hole drift velocity, and the same pattern is observed even with the benchmark values, and the same pattern is observed with diffusivity. Electron diffusivity is higher than hole diffusivity, and the same pattern is observed in the least square fit BCP model, which is the benchmark values. In conclusion, the SINDI algorithm is used to predict the equations of charge transport and the parameters from data. For the charge transport problem, the parameter estimation is really sensitive with data resolution, and it is highly accurate when the data resolution is above 90%, and as the resolution decreases, the accuracy also decreases. With the experimental data, the PD discovered was correct, but the coefficients lacked accuracy. But it was able to provide important insights about the phenomenon. For example, it correctly identified that the hole drift velocity is higher than the electron drift velocity, and that the electron diffusivity is higher than the hole diffusivity. Although the parameters don't match the benchmark parameters exactly, the important underlying patterns of the physical phenomena are well preserved. So this highlights the efficacy of the model for rapid qualitative analysis at only a fraction of the computational cost that is required in case of traditional computational models. So for the people who stuck till here, there is a bonus for all of you, and this is a teaser to my upcoming video where I use physics informed linear transformations for estimating the total charge in dielectrics. Here I have PA measurements, and using the model I directly estimate the total accumulated charge. So stay tuned and stay curious. Thank you.